Alright guys, it is now time to talk about section 4.6. Section 4.6 is actually going to be split into two parts. This is part 1, where we are going to start to talk about limits at infinity. And we're going to talk about asymptotes. That's what we are going to be doing in part 1 here. So we're going to start first with a definition, as we normally do. If f of x gets closer to something, I'll just call it L, as x becomes increasingly larger, then we say the limit as x approaches infinity of f of x is equal to L. Again, here I just want x to get really, really, really big. Okay, as that happens, I approach something L, then we say it is equal to L. On that same note, if f of x excuse me, gets closer to L as x gets increasingly smaller, and by smaller I actually mean in the negatives, we say the limit as x approaches negative infinity of f of x is equal to L. So what I want to do here is see what happens as x gets really, really large, and then also what happens as x gets really, really small. That's what we are going to be looking at here in section 4.6. So let's do some examples. Let's find the limit as x approaches infinity of 5 minus 2 over x squared. Now, what I know from way back in chapter 2 is that I can actually split this into two things, right? So I can actually look at this as the limit as x goes to infinity of 5 minus the limit as x goes to infinity of 2 over x squared. Now, this first part here isn't that hard, right? Because as we know, since it's a constant, it's just going to always be that constant, right? So this first part is just a 5. That isn't bad. It will always be 5, and so I get 5. Now, looking over here, this isn't a number I can actually plug in, right? Because that's normally what we like, is to see, okay, can I plug this in and get a number, right? Well, that's not a number I can plug in. So I have to think about this, okay? Remember, what this is actually trying to say is as x gets really big, okay? So as x gets really big, let's look at what happens to x squared. Well, if I square a thing that's really big, that's going to also be really big, right? So what this is 2 over something that's really big, okay? Well, 2 over a number that's really big, let's see what happens there, okay? So let's just see what happens if I do 2 over, let's do something really big, 100. We get 0.02, okay? Well, now let's go even more than that. Let's do 2 over 1,000. What happens there? 0.002. Okay, let's do 2 over 10,000. Even more so, that would be 0.0002. So my point here is as I do 2 over something that's really, really, really big, the entire thing is approaching 0. So this is going to be 5 minus 0, which is 5. So the answer will be 5. Again, that is because if I do 2 divided by something that's really big, the whole thing is going to get really small. Let's think about it if I was doing the limit as x goes to negative infinity. Well, notice the only x here is this x squared, right? So what this is 2 over a negative squared. Well, a negative squared is positive. So this is actually the same thing as the limit as x goes to infinity. Again, the reason why is because the only x I have in here is being squared. So that makes it positive. So it's the same thing, which we already found is 5. So the point I'm trying to make here is that a lot of this isn't really plugging in stuff or that kind of thing. It's a lot of having to think about it, okay? Like thinking about this. 2 over a thing that's really big is actually small. Same thing over here. I'm squaring a negative, which makes it positive. So that's why these are the same thing. All right, let's look at some other examples. Let's do, for example, the limit as x goes to infinity of 3 plus 4 over x. Let's think about that. All right, so the only x I see is this one right here, okay? So the 3 just stays 3. So 3 is always 3, that just stays 3. But if I plug in a thing that's really big over here, what that'll be is 4 over something really big. And as we just saw, doing 4 over the thing that's really big actually makes it really small. So that's like adding 0. Just to see that a little bit more, just so that is absolutely clear, let's say I graphed 4 over x, okay? Which is just this part right here. Let's say I graphed that. Looking at this graph, as x gets really big, look at what happens to the y. Y is getting really close to 0, right? That's why I get this. Again, it's because if I do 4 over a thing that's really big, the whole thing is actually small. So I get 3. I get 3 there. Let's take a look at negative infinity. Now for this one, I can't do what I did on the last one because that's not being squared. So it does not just become positive, okay? But the idea is still the same. This is going to be still a number that's really big, just negative, okay? But it's still 4 over a thing that's really big. So this is still approaching 0. So the answer I get will be 3. Again, because it's still 4 over a thing that's very big, it doesn't matter what the sign is because it's still big, right? Same thing if I looked over here. If I go really far to the left now, I see it's still 0. Let's take a look at one that might make a little bit more sense when we think about it. Limit as x goes to infinity of, let's do 3x squared plus 5x. Let's see about that. Well, let's think about this, okay? As x gets really big in here, a thing that's very big squared is still very big. Again, plus 5 times the thing that's very big, right? So what's going to happen here is this will just grow and grow and grow because x is going to get really big. So this is equal to infinity. Again, because x will just grow and grow and grow and grow and grow. Let's take a look at negative infinity and give that a good think. Now, for the first part right here, I have x squared, so since that's being squared, that can become a positive, right? But I can't just write that this is the same as positive because this one's not being squared. So it doesn't work like that. We can't just do that. So again, I have to think about this. Notice this term is being squared, which means a number that's really big is going to grow more with this term than it is with that term, because this one is x squared, and so that's going to grow and grow and grow, whereas that is just an x. So even though this will grow and grow, it's going to grow a lot slower because it's not being squared. Okay? So as x grows, this term isn't really going to change a whole lot because the first term is growing a lot quicker because it's being squared. So when I do these, the really cool thing is I only have to worry about the highest power because that's growing the fastest. Okay, so I only need to look at 3x squared. So if I look just at 3x squared, the x there is being squared, and so this becomes positive. Therefore, it approaches positive infinity. Again, I know it's a little strange, but if we think about this, this x squared term is going to handle a lot of what's changing because it's being squared, and so it's going to change quicker than this term right here does. Okay. Again, we can draw this graph just to make sure. If I did the graph of 3x squared plus 5x, as I go really far to the right, which is positive, I see it's going up and up and up and up and up, which is why I get that. If you look on the left side, it's going up and up and up, which is why I get that. Again, we only need the largest term there to let us know what's happening. So with that in mind, let's do this example here. Let's find the limit as x goes to infinity of 4x cubed minus 3x. So like we said, since this is going to just grow and grow and grow, I only need the largest power, right? X to the third is going to grow way quicker than x. So I don't really even need to look at this term right here. I only need the first one. So let's just look at the limit as x gets really big of 4x to the third. Well, I can tell here as x grows and grows and grows, x to the third is going to grow and grow and grow too, right? So this is just going to approach infinity. Let's do negative infinity now and see what happens there. Once again, as we've said, I only really need the x cubed term because that's going to grow way quicker than 3x does. So again, I only need this first term. So that's the limit as x goes to negative infinity of 4x to the third. Now let's think about this. A negative being cubed is still what? A negative. So this one's going to be negative infinity because it's being raised to the third. Whereas on the last one, it was being squared, and so that's going to make it positive. This one is being cubed, and therefore it's going to stay negative. Now, where this is really helpful is when you see some like this. So let's do the limit as x goes to infinity of 3x squared plus 4x minus 2 over 5x squared plus 9x minus 1. Let's think about that. Now, like we have said, I only care about the largest term, right? So looking on the top, the only one I really need is this x squared term because that's going to grow quicker than 4x and 2 do, right? So I'm going to only need the 3x squared on top. On the denominator, again here, x squared is going to grow quicker than 9x and 1 do. So I only need 5x squared. So I just have to look at 5x squared. Well, the good thing about this is both of those have an x squared, so they cancel out. So I'm really left with the limit as x goes to infinity of 3 over 5. Well, that's a constant, so the answer that I get is just 3 over 5. 3 over 5. Now let's look at negative infinity of the same thing. Once again, I only need the largest one for each. So on the numerator, I only need 3x squared. Down here, I only need 5x squared. Everything is being squared, and so I can rewrite this as a positive because they're both being squared. So that's the same thing as the limit as x goes to positive infinity, which we have already seen is equal to 3/5. Again, the reason why I can just write this as a positive here is because everything is being squared, so it will always be positive. All right, let's look at some more examples that are kind of like that. The limit as x approaches infinity of 3x squared plus 2x over 4x to the third minus 5x plus 7. Let's look at that one. So the same thing, I only need the largest one on each. On the numerator, the largest term is 3x squared, so we only need 3x squared. The denominator is 4x to the third. We can reduce this since there's x squared up here and x to the third here. That cancels out and gives us just 3 over 4x. So now, again, this isn't a number I can plug in, and so I just have to think about it. If I do 3 over 4 times a number that's really big, that's going to be 3 over a thing that's really big. And as we have seen, that would make it approach 0. So that's what I get there. If I'm looking at negative infinity, it works the same way. I'm just rewriting it. 3x squared plus 2x over 4x cubed minus 5x plus 7. Again, I only need the largest one. So 3x squared over 4x cubed, and we already know that reduces down to 3 over 4x. The thought with this one is the same thing, okay? So even though this is negative, it's still going to get very big, right? So 3 over a number that's really big, doesn't matter what the sign is, it's still going to approach 0. Another example. I think I can make it fit. You know what? I'm not going to risk it. I'll just erase a new board. Another example. Limit as x approaches infinity of 3x squared plus 4x over x plus 2. So let's think here about this. Again, I only need the largest one. The largest one on top is 3x squared. Largest one on the bottom is x. I can cancel out 1x, which gives me the limit as x goes to infinity of 3x. Well, that's 3 times a thing that's really big, which is going to be very big. So that's going to give us infinity. Looking at negative infinity, just rewriting it, 3x squared plus 4x over x plus 2. Again, we only need the largest ones. That's going to be 3x squared over x. Cancel out an x, just like we did. Limit as x goes to negative infinity of 3x. Well, this one is very big too, but in the negatives, right? So that's going to be negative infinity there. Again, because even though it still gets very big, it's going to be in the negatives. So that's why we put that. Another example that I really like, I'm going to get another board for this one as well. This example is really good. This is going to be the limit as x goes to infinity of 3x minus 2 over the square root of 4x squared plus 5. So let's think about this one. Once again, just like we have done, I only need the largest ones on the top and the bottom. So on top, that's 3x over. On the bottom, this one seems a little strange, but on the inside, the largest term is 4x squared. So what I care about the most is the square root of 4x squared. Well, what's really nice about that is we know that the square root of 4x squared, square root of 4 is 2, the square root of x squared is x. So this is the same as the limit as x goes to infinity of 3x over 2x. X's cancel out, so we're left with just the limit as x goes to infinity of 3 over 2. That is a constant, so 3 over 2. Positive 3 over 2 there. Do the same thing for negative. This one actually does require a little bit of extra thought, and we will talk about it as we get there. 3x minus 2 over square root of 4x squared plus 5. Again, we only need the largest terms. Limit as x goes to negative infinity of 3x over the square root of 4x squared. Now, we need to stop and think right here, okay? This is where it needs a little bit more thought. Up here, everything was positive, right? So I didn't really need to think about this. This one is not. So if I plug in a negative right now, the numerator would be negative, right? But the denominator, since it's being squared, would be positive. So what I need to make sure will happen here is that what I end up with is going to be a negative. Because when I divide a negative by a positive, I get a negative. So I need to make sure that happens, okay? So even if my math works out to where I get a positive, because of what I see right here, I know my answer must be a negative. So now I can keep on. Same thing, same thought. Limit as x goes to negative infinity of 3x over, that becomes 2x. Cancel it out, and we normally would get 3 over 2, but as we saw up here, negative divided by a positive is going to be negative 3 over 2. So just be careful there. Let's do a little bit more complex of a problem. Still isn't bad. Still want to make that very clear. It still isn't bad. It just requires a little bit more thought, kind of like the last one did. Limit as x goes to infinity of 2 plus 3 e to the x over 7 minus 5 e to the x. All right. So let's think about this now. Remember what I said was that I only need the largest term for each of these, right? So what the harder, quote unquote, harder part of this is to see which one of these is the larger term, okay? Well, x is getting really big and it's always going to be positive. And so e to something that's really big is going to end up being really big, right? E to something very big is something that's very big. So this 2 is smaller than this 3e to the x. So the largest term on the numerator is 3e to the x. Same thing right here. E to something that's really big is going to be something that's very big. So the larger term on the bottom is a negative 5e to the x. Well, what's so neat about that is e to the x will cancel out. So I'm just left with negative 3/5. That one isn't too bad. But let's see what happens when I make it a negative. So now I have e to the power of a negative, right? Well, what I can actually do is, since this power is going to be negative, I can put it in the denominator, right? So if I wanted to make this positive, because that's not as hard to work with, I can make this positive, limit as x goes to positive infinity. And since this is in a power, I can put it in the denominator. So 3 over e to the x, 7 minus 5 over e to the x. Again, I can do that because I'm making my power the negative. Okay. Well, now e to something that's very big is going to be very big. 3 over a thing that's big, as we have said, approaches 0. So the larger term on top now is this 2, because this term is getting really small. So that's going to become 2 on top and 7 right here. So that's going to be 2 over 7. So that's the harder, again, quote unquote, harder part whenever I have e's there, is because if I have e to a power, the minus sign actually puts it in the denominator. Okay? So just be mindful of that. There's one more example I want to do before we move on. This one also requires a little bit of thought, but still is not bad. This one's actually very cool. I think it's cool. Let's do the limit as x approaches infinity of sine of x over x. So like I said, this one requires a little bit more thought. So looking in the numerator, okay, let's think about what sine does. Sine is always going to be between -1 and positive 1, right? This is always going to be between -1 and positive 1. We can see that if you look at the unit circle. I have one on my desk. I'm pulling it out. The sign is the y, right? So if I look at all the y's, the largest it can possibly be is a 1, and the smallest is the -1. It will always be between those, okay? So knowing that, we know the numerator does not grow pretty much at all because it's going to stay between two things, okay? But the denominator, as we see right here, is going to get very large, okay? So what I have then is something small, because this is going to be between -1 and 1, over something that's really big. So as we have seen, that's going to approach the 0. All right, so now that we know how to do that, you may want to know, okay, why does this help me out? Well, when I draw the graphs, this actually helps us see what happens as my graph goes far to the right and far to the left. So we can now tell what the end behavior is. So first things first, if the limit as x goes to infinity of f of x is equal to L, or if the limit as x goes to negative infinity of f of x is equal to L, then there is a horizontal asymptote at the horizontal line y equals L. So if I can get a number for L, then I know the horizontal asymptote is at y equals L. If the limit as x approaches plus or minus infinity of f of x is equal to plus or minus infinity, then we say there is no horizontal asymptote. It'll just grow and grow and grow. And lastly, if the limit as x goes to positive or negative infinity of f of x cannot be found, it has oscillating behavior. That's kind of like what sine does, because for sine, as x grows and grows and grows, it's just going to go from here, and then it's just going to rotate again, and then rotate again, and then rotate again, and then rotate again. So it's not approaching one thing, because it'll just switch off and on from all of these. And you can tell that by if we graph the sine function. If we look at sine of x, it has this graph right here, which means it's just going up and down, up and down, up and down forever and ever and ever. So that's kind of like what sine does. So let's look at some examples of determining the end behavior. Example. Let's look at the function f of x equals 3x squared plus 5x minus 8. So first things first, to know what happens on the right side, we do the limit as x approaches infinity of f of x. So 3x squared plus 5x minus 8. Well, as we have seen, I only need the larger term, right? So I only need 3x squared. So the limit as x approaches infinity of 3x squared. And as I know, a thing that's very big squared is going to be very big. So that's going to go off to infinity. So what this means is when I draw the graph, on the right side, it's just going to increase forever and ever. That's what that means. To know what happens on the left, let's look at negative infinity. Again, we only need the larger term, which is 3x squared. A negative squared is going to make it positive, so this one is also positive infinity, which means on the left side, it will also point up. Therefore, I can say there is no horizontal asymptote. There's not one. Let's do the same thing with another example. This time the function is going to be f of x equals 2x cubed minus 4x squared minus 3 over 4x cubed plus 10x minus 1. Again, to know what happens on the right, do the limit as x goes to infinity. We only need the largest for each of these. So the largest on top is 2x cubed. Largest on the bottom is 4x cubed. Cancel those out. 2 over 4 is like saying 1/2. So this means there is a horizontal asymptote at y equals 1/2 on the right side. So now looking at the left side, do the same thing but negative infinity. I'm just rewriting it. 2x cubed minus 4x squared minus 3 over 4x cubed plus 10x minus 1. Again, we only need the largest one, negative infinity. So on the top, that's 2x cubed. On the bottom, that's 4x cubed. Remember, since my sign has switched now, I've got to think about this. A negative cube is going to be negative. Same thing right down here. A negative cube is going to be negative. Negative divided by a negative makes the whole thing positive. So this is going to be positive. Again, 2 over 4 is 1/2. So the same thing will happen on the left. So on the right and the left-hand side, we have a horizontal asymptote at y equals 1/2. I have one more example. Do the same thing. This time the function is going to be f of x equals 3e to the x minus 4 over 5e to the x plus 2. To know what happens on the right side, do the limit as x goes to infinity. On the top part, since this is going to be positive, my larger term is 3e to the x. Again, because e to something that's very big is going to also be big. So 3e to the x. The bottom, the same thing, 5e to the x. E to the x cancels out, so we just have 3 over 5. So on the right side, we have a horizontal asymptote at y equals 3 over 5. Now for the left side, do the same thing, negative infinity, 3e to the x minus 4 over 5e to the x plus 2. As we did see, since this is going to be negative, this is like having 3 over e to the x. So as my x gets very big, this whole term gets really small. So my larger term on the numerator is negative 4 now. Over the bottom, do the same thing. My largest term is going to be 2, so over 2. Negative 4 over 2 is negative 2. So on the left side, we have a horizontal asymptote, but this time it's at y equals negative 2. So what this means for the graph then is that y equals 3 over 5. If this is 1, then 3 over 5 is like right here. And then at y equals negative 2 right here. On the left side, I'm approaching this line, but on the right side, I'm approaching that line. That's what that means. In part 2, we are going to learn more about how I can use everything we have learned so far to draw a graph. So I will see y'all then.